Good morning, everybody. My name is Alan Eberhardt, and I'm sitting here in my kitchen where it's nice and white and bright to lead you on a virtual tour of my lab and then take you on an experimental journey. So I'm going to share the screen here and get into a PowerPoint mode, and we'll get her done, as they say. Okay, so I'm a professor and associate chair in the Department of Biomedical Engineering, and I'm director of the Experimental Biomechanics Core, or what we just call as the Biomechanics Core. So I'm going to take you on a virtual lab tour, and then we're going to end up with an orthopedic device experiment. And this is a real-world orthopedic device experiment. So if you walk down the Hohen building, walk down the second floor of the Hohen building, that is, you'll come to room 270. And if you peek around the corner, you will see a room full of mechanical testing equipment. And so if you can see my mouse here, that on the left is a mechanical testing system called an MTS. Basically, that's a push and pull device. So the piston moves up and down. And that is a load cell that measures forces. So we capture forces and displacements. And those are used for high force applications like orthopedic implants. This center device is called a Bose test bench. It's also a mechanical testing system that pushes and pulls and records forces. But this is done on very small specimens, ultra low forces. So we have gram level forces and micron level displacements to do things like indent mouse cartilage. This over here is a drop tower. This is for impact testing. We've done a variety of impact tests on human pelvis to determine fracture tolerance of human pelvis. So in our lab, essentially we have high and low force mechanical testing equipment, also impact testing and wear testing. I didn't show you that device, but we also can do wear testing. And essentially we do orthopedic biomechanics research, which includes both hard and soft tissue, mechanical property determination, as well as the studies of implants and devices. Just some research examples that I pulled out of my notes here. This on the left here is an example of a proximal humerus plating technique. This is the humerus is your upper arm bone, and this is for a plating technique for highly comminuted or very severe fractures, and they're interested in understanding its response to an applied force. So in this case, the load is applied down here and the displacement is measured. And what we typically do with such data, and this is what I'm going to ask you to do, is we will plot the load versus the displacement and determine the stiffness of the construct, and sometimes also then we'll be interested in the maximum force. On the right over here is a 4-point bend of that's actually a dog tibia. We were doing a study on various medicaments, essentially things that would be added to a fracture site to help it heal. So these are examples of simple kinds of tests. We also do some more complicated stuff. This was an example of a human pelvis. That is a cadaver pelvis taken from a real person. Where we were simulating a single-legged stance in the presence of metastatic lesions. So on the right over here is a computer model which shows where the lesion was, sort of right behind the acetabulum here, right behind the hip joint. This is a common place to get these lesions, and we were interested in what was the effect of the location of the lesion, the size of the lesion, and a technique called percutaneous acetabuloplasty, which is essentially filling them full of bone cement to repair them. So these are just some examples of what we do in our lab. So now I'm going to take you on an orthopedic device application, and we're going to do an experiment, or essentially show you an experiment. Severe long bone fractures, such as the humerus or the femur, are often repaired by use of intermedullary rods. So your humerus, that's a long bone, that's your upper arm. Your femur, your upper leg bone, your tibia, these are the types of bones that if severely fractured, you can't just put a cast on it. You have to do something more sophisticated. And over here, we see an image of an intermedullary rod that is placed down the intermedullary canal of the bone and then fixed with cross pins. And then this allows this will carry the load then and allow this bone to heal. So you can see this was a very severe fracture, which in this case requires an intramedullary rod. Now, one aspect of these rods that is of interest is, can we eliminate these cross pin sites? Because every time you have to add one of these cross pins, which are added to produce torsional and compressive stability, you have to add another surgical site. So there's another drill going through the leg here and through the bone. And so the question is, can we get rid of these secondary surgical sites by coming up with some alternatives? So we're working with a company that has what's called a deployable set of talons. So there's a tool that goes down the rod and you twist it and out come these talons. I'll see if I can demo here. So they out come the talons and they grip into the bone. And the idea is that they are to replace one end of cross pins. And so here are the cross pins on the other end of that device. And the question is, do these talons resist the compression and torsion forces as well as the pins? So the experiment that we would do if you were in the lab, but I'm just going to show you what we did, is we took these rods and we deployed them in synthetic bones. So here's a synthetic bone and you can see the cross pins and there's the rod. And then we turned it around and the talons are deployed and you can just see little dots where the talons have actually poked through the bone. And then we basically compress these using our MTS machine in the direction of the arrow the forces are applying down. And so force and displacement are measured and then we can do our calculations. So the MTS is controlled, has a computer controller, and this is basically the user interface. Compression, the displacement rate is prescribed, the load cells measure the forces, and then linear variable displacement transducer measures the displacement. And it all comes out on this screen and is recorded by the computer. So the way we output that data then is that you will be interested in plotting the load versus displacement curves from which you will determine the stiffness K. And that is relates to the equation F is equal to Kx, which is that of a simple spring. So if you imagine a spring attached to a wall, which has been stretched out a distance x by a force, then the linear relationship between F and X is the slope of that line, and that's K. And so you have the F equals Kx relationship, y equals mx plus b, your old algebraic equation. So F is equal to Kx since the y-intercept is 0. And we can do other things like calculate the work done or the potential energy stored as 1/2 Kx squared. So that's the concept, the physical concept behind the test. So your task is now to use the attached spreadsheet data to determine the stiffness of the talons and compare them to the pins. So how do the talons compare to the pins? And then what I want you to think about is, why would stiffness in compression be important for fixation of a femur fracture? Okay, so that is your task, and there should be a spreadsheet attached somewhere that you will find. And here's what your output data should look like. So when you plot force versus displacement, you're going to get a graph that does something like this. And so we loaded it up, and then at this point we basically stopped the displacement at 10 millimeters. So what you're interested in then is finding the slope of this part of the curve. And what you're immediately going to say is, well, that's not a straight line, and that's typical of the real world. Nothing comes out to be a straight line. And so what you might want to do is to find an initial stiffness, say, or perhaps a secondary stiffness, and compare those. So good luck.